Okay, Ani is the local expert in SpringSaLaD, so he's going to tell us a little bit about that. And again, this was predicated on the idea that anyone who wants to use SpringSaLaD will have gone through the YouTube video that Ani produced a couple of years ago. So anytime anyone wants to jump in and ask a question, that's perfectly okay.
Yes, so hello everyone, I'm Ani Chattaraj. So today what I'm planning, I'll just present maybe 3 or 4 slides, and of course if you have any question, please feel free to ask in the meantime. So the first important stuff about SpringSaLaD is this idea of scale of the simulations, right? So depending on the problem you're interested in, you might want to use different kind of tools. So this is on the left hand side, we have this atomic level resolution where people usually use like molecular dynamics type of tools. On the another extreme, we have this cellular scale where people typically use virtual cell or Copazi. And in the middle, we have this interesting scale called mesoscale, where we have this filament formation, signaling cluster, and there's this whole field of biomolecular condensates. So for this type of systems, SpringSaLaD would be a suitable tool. So to a little bit more about SpringSaLaD, that let's say if this is your protein of interest. So in this particular example, we have a protein called NCK. It is a signaling protein molecule, which has this 1 SH2 domain and 3 SH3 domain. So in SpringSaLaD, we will model in this particular way. So for example, we would model this entire domain represented by a spherical ball, and they will be connected by a stiff spring. Okay, and you can also put a bunch of linker sites also to mimic the actual structure of this whole sequence. So unlike molecular dynamics, there is this idea of the springs transmitting the force. So obviously, in order to move, you need to experience some kind of force. So the force experienced by a site is a vectorial sum of all the springs that are coming from the neighboring sites, and also there is a random force to mimic the Brownian motion sort of thing. So here is an example. This is a typical kind of problem that you want to model using SpringSaLaD. So we have this 2 type of molecules here, tetravalent, let's say A and B, this magenta and the green. And like Michael described yesterday, SpringSaLaD also uses a binding rule-based scheme. So you just need to say 1 SH3 will bind to 1 PRM, and you give the K on and K off, basically, right? And all the possible interaction will be taken care of by the software, basically. And this is also spatial simulation, so the molecules are diffusing in space. So once they find one another, the software computes a probability based on this K on and K off, and also the diffusion and a bunch of other stuff. And that's how it triggers the binding and unbinding reaction, essentially. So that's the overall scheme of the software. And I have some examples as well, but at this point, I would just stop and ask you if you have any question for this particular section. No? Okay, so maybe I'll just go to my next slide. All right, so with SpringSaLaD, we can ask a lot of interesting questions on this molecular scale. So here is an example. I'm showing how to mimic the structural flexibility of a molecule. So let's say you have some protein molecule, and these are the 2 sort of binding domain or biochemically active domain of that proteins. So how do you model that protein, right? So you can, the number of sites sort of decides the overall compaction of the flexibility of the molecule. So here I'm showing the distance between this ball and this ball is a function of time. And on the right hand side, I have the radius of gyration. So radius of gyration essentially computes the compaction of these molecules as a whole. So as you can see, as a function of number of this pivot sites, PS, as you increase the number of pivot sites, the distance, the steady state distance sort of gradually goes down, and the radius of gyration follows the same trend. So what it's telling you that if you if you want to make this particular stretch more flexible, you put more and more linker sites. And beyond some point, you cannot make the molecule more flexible. At that point, it's absolutely flexible, basically. So there is obviously a trade-off. So in order to make it more flexible, you can play with this linker sequence to tune in the rigidity or the flexibility of the molecule of your interest. And obviously, you can, as I mentioned, you can model the molecular geometry and flexibility, and also by tuning the size of the ball, you can also play with the steric interaction of the system. And obviously, if you watch the video, you know that there are multiple type of reactions that you can specify, such as state transition, the allostatic transitions, and so on. So this was one of the important update that came about last year, I think. So for example, if you are defining a binding reaction, right? So for example, you are defining SST domain of NIC would interact with PRM domain of NWASP, and then you define this on rate and off rate. Previously, there was no bound that what should be the numerical value of the on rate that you can enter into the software. However, there is a physical limit that which you should not exceed in order to get a numerically accurate result. So that has been taken care of. So that's an important update. So the rule of thumb would be the theoretical value of your k-on should not exceed this number of 4 pi rd, where r is the summation of the radii and d is the summation of your diffusion of the two sides. So that's an interesting thing to keep in mind while setting the parameters of your biochemical reaction. And here is I'll share one example from one of my projects. So here I'm trying to model is a 3-component system I have. So this is one protein called nephrin, which has these 3 phosphotyrosine sites, and other sites are there to mimic the actual structure of the molecule. And here I have this NIC molecule with 1 SH2 domain and 3 SH3 domain. And here I have another molecule called NWASP with these green balls represent the proline reach motif, right? And here are my binding rules. So SH2 can interact with phosphotyrosine, and SH3 can interact with the proline reach motif with certain affinities. So that's a snapshot from my SpringSaLaD visualization window. So this is the situation at the beginning of the simulation. So all the molecules are stretched out, and this little yellow patch represents a certain section of the membrane. So since nephrin is a transmembrane protein, is a receptor protein, you can attach that molecule into this two-dimensional surface, right? While NIC and NWASP can diffuse in the 3D space here. However, due to this binding interaction, after some time, they will interact with each other, and most of the molecules would be recruited near the membrane. So to study this type of clustering process, so that was sort of the original motivation behind designing SpringSaLaD, that you can really sort of probe the structural features of the molecules in order to understand the clustering, right? So for example, you can ask questions like, what happens if you make one of the molecules more flexible or less flexible? So here in this example, I'm showing you 3 different sort of construct. The A is the sort of the one that I showed you before. In B, I just removed this intermediate linker site. So B is less flexible than A. C has similar flexibility than A, but I made the linker sites little smaller. So the steric interaction should be little less, but not too much. But for D, I removed this, this terminal bulky sequence. So it is sterically much more accessible than B. So now if we see the clustering distribution for these 4 different configurations, we see that going from A to B, there is a upward shift of clustering. So that means the less flexible molecules have more tendency to cluster, which makes sense if you think in terms of the entropic effects and so on. But A and C has almost similar clustering behavior, suggesting that flexibility is supposedly the key player here. Since A and C, they have almost similar flexibility, their clustering propensity is also similar. But now, interestingly, if you go to D, you see the clustering is very dramatically different, right? So then we don't have those steric sites, those terminal bulky steric sites. So now these binding sites are much more accessible to its binding partners. So that's why we see this higher level of clustering here. So this kind of questions, basically you can ask using this tool, that this is one particular feature, that this structural feature, how does those feature affect the overall clustering behavior. So here is another example I'm going to share. So here the idea is, as I mentioned, that we have a 2D membrane, and then there is the Z direction here, which make this whole three-dimensional reaction volume. So we can change the aspect ratio in such a way that the overall volume of the system remains constant. So for example, the blue case, we have 100 nanometer in XYZ, all three direction. In green situation, we have XY 50 by 50. However, Z direction is 400 nanometer. So although the overall volume is fixed, the surface density of the receptor molecule is 4 times higher in this case than this case, right? And the clustering behavior is equally interesting. We see that the blue case is here in our so-called reference system, and the red and green ones, they are showing this very high level of clustering, although due to this geometrical manipulation, the time it takes to reach the steady state, that's also changing, because now we have this very long z-axis. So the molecules need to diffuse in this along this long direction in order to find one another. So they take longer to reach the steady state, but once it reaches the steady state, it converges to a very high steady state. So it highlights the importance of this membrane recruitment effect. So the reactions that are happening at the bulk in the 3D volume versus the reactions that are happening on a 2D surface, right? So due to this confinement, there is this higher local concentration, which promotes this clustering behavior of the system. And obviously it has important implications in signal transduction and so on. As a control, if you remove the nephrine from the membrane and do this kind of geometric manipulation, we see that we don't see any significant result at all. So it was really this membrane anchoring that drives this effect, and SpringSaLaD enables you to probe that kind of effect, essentially. So I think that was my last slide. So probably I'll stop here. And in the meantime, if you have any question, please feel free to ask.
So I have a question I just thought of.
Yeah, sure.
If you don't mind, Ani. Do events in SpringSaLaD. So if you wanted to look at sort of how those complexes change if you introduce something new into the system, a competition for binding or something like that, or a change in the state of one of those molecules, can you sort of because you've been usually showing things run to steady state, can you then have an event which will interrupt and see how the system relaxes?
Yeah, in principle, it should possible, but so far SpringSaLaD does not have that functionality, like to trigger an event at a certain time point. One way to do it is basically you have to initialize your simulation and relax to a steady state, and then maybe start another simulation with desired perturbation or something. But right now, like vCell or Copazi, we don't have a systematic way to introduce a trigger at a certain time point. Currently, we don't have that.
One thing that I thought might be informative, I don't know how fast you can find this in your collection of PowerPoints, Ani, but we've been talking a lot about when it's important to do stochastic simulations versus deterministic simulations. We talked about that a lot yesterday.
Right.
And all of the SpringSaLaD simulations are stochastic.
Right.
And
yeah.
you showed in all of these examples that you showed sort of the average of, like 100 simulations or something like that.
Mm-hmm.
But one of the things that I know you found in looking at the histograms of clustering is that you actually, if you look at the individual histograms, you can get different kinds of you can get some insights that you can't get from looking at the average histograms from many runs.
Yeah, so this is
So-
like, this would be sort of like a one example of that thing. So I mean, maybe I should explain so this is like, I have, like a pair of molecules. This is A4 and B4. So one of the ideas is that one of the magenta side can interact with one of the green side. And here the idea is we have these two sort of binding reactional rules. One rule will inject molecule into the simulation box. Another rule would inject, take molecule out of the simulation box. We have this creation and decay. And at any idea here is that these rates would be high enough so that at any time point, the concentration of the monomer would be fixed, right? So this approach, we call it clamped monomer concentration. And here, Masles was talking about the idea of stochasticity. So here you see that without going into the biophysics behind it, this is the average behavior. Let's say this is the average behavior of 100 trials. So you can see, just looking at this average, you can still see the fluctuation bar. So you can see that if you take the fluctuation bar into account, you can see something interesting is happening. But once you inspect the individual trials, then you see that something really interesting going on, that some of the runs or some of the trials are sort of going up exponentially as a function of time. This is the total concentration of A and B as a function of time. But some of the trials they are sort of fluctuating around a lower steady state, right? So some of them are going up, but some of them are fluctuating in the lower steady state. So that's why once you take the average of all of these, that's why you get this huge fluctuation bar around their average or mean values. And that's happening because of these are all stochastic simulations. So once these clusters fit into a sort of right seed or a right there is a nucleation step here, and that nucleation step itself is a stochastic process, right? So that's why this dynamics of cluster growth, they also shows a considerable degree of stochasticity. So that's another important aspect of any stochastic simulation in general, and SpringSaLaD can capture that effect as well.
So it's very important to look at individual, and you saw this a little bit yesterday too when Pedro described that bistable system.
Yeah,
it's important to look at the individual trajectories, not just at the average of many runs, to really understand what's going on.
Yes, it's the individual runs as distribution. If you look at the third distribution, actually, you see that it might die out completely. It can actually explode, stay on the lower steady state, or even die out.
Right, right.
Mm-hmm.
Yeah, I don't think we have time, but there are other examples of looking at the histogram of cluster sizes, where the average histogram shows that sort of a continuous sort of distribution. But if you look at the individual histograms, you see that there are just one large cluster in any given run in equilibrium with a few small clusters. So that's another example. But I think we're at the end, unless there's a burning question that somebody has come up with. We'll move on to a discussion of parameter estimation. Any other questions? Okay, parameter estimation.
Yes, can I ask two questions?
Sure.
Okay, so I noticed like at the beginning of your simulation, all the polymers, they are kind of all perpendicular to the membrane surface. Is it necessary?
No, it's just that the way the default state is defined within the software. So they all start with a stretched out version of the molecule, right? So they all appear linear, but they're actually not linear because they can bend around in each other. And the way to place the molecule is the way it's written right now. It places the molecule along the z direction.
Okay.
But that is obviously, it's a random placement, so that does not have any sort of major significance on the steady state behavior of the system.
Okay, okay, nice.
Yeah.
And another one is when you wanted to see the one of your you wanted to see the membrane and influence of the cluster effect during the simulation, and you keep the system volume fixed, but you decrease the membrane area.
Yeah.
So did you try to further decrease the membrane area? I suppose at one certain point, because of, you know, those polymers, they are too crowded, so
Yeah.
maybe there's no way for them to get a, you know, more molecules bound to them.
I
Is it possible?
think you're right. Yeah, at some point it will hit the sort of packing fraction of the molecules that you cannot put any molecule inside that, right? So I think there should be a sweet spot essentially. Initially, you would see higher clustering with higher density, but then you would hit a point that crowding will take over, I think. So I think there has to be some kind of a balance there as well. Yep.
Nice. And one more.
Yeah,
Is it possible for me to ask? I know there's a mathematical problem I haven't. I know you haven't mentioned, but I want to ask you. I know that SpringSaLaD used the method of Urban-Chapman's method, right? So there are two reaction like radius. One is called a bonding radius. The other one is unbounding radius. You know, and their value is kind of different, I remember. So when two sides they react with each other, you put them, you know, closer to each other as the distance as the bonding radius. Mm-hmm. So next step, let's say they unbound. So you need to move them further, right?
Yeah, I think in SpringSaLaD the way I think it's same. I think the binding and unbinding radius, while solving the, you know, the partial differential equation with the boundary condition and everything, mm-hmm. the condition is the binding radius is equals to unbinding radius.
Equals, okay, nice. Then
yeah.
No problem. Okay,
yeah,
cool.
Yeah. So if you see the supplementary information of the SpringSaLaD, you know, Dr. Michalski derived the equation, and in one of the condition he says that, you know, the reaction radius is equals, binding radius is equals to unbinding radius.